Welcome to this explainer. Today, we're going to dive straight into the fatal errors that quietly cost Cambridge AS and A-level physics students their top grades. I want you to picture this. You're sitting in the exam hall, the clock is ticking loudly, and you see a seemingly straightforward question. You start writing immediately, but right there, literally in the very first line of your answer, a trap springs. Imagine plunging straight into a calculation without defining the physical mechanism first. It's a classic trap, and we're about to totally dismantle it. You see, 9 out of 10 students get this wrong in exactly this way. They write down a formula, plug in the numbers, and totally ignore the context. And just like that, poof, the method marks vanish.
But once you see where that error creeps in, the correct method becomes basically impossible to forget. So let's rebuild your understanding step by step. The absolute secret to mastery in Physics 9702 isn't just memorizing equations, it's visualizing the physics before you ever touch the math. Because if you can see the cause and effect relationship in your mind's eye, the math just naturally follows.
All right, Section 1, Mastering Measurement and Errors. Let's dive right into this first massive hurdle. It might sound basic, but honestly, this is the foundation where examiners constantly test your actual scientific reasoning, rather than just your ability to read a ruler.
First up, we absolutely have to distinguish between accuracy issues and precision issues. A systematic error is a constant shift. Think of a zero error on a micrometer. That shift reduces your closeness to the true value, which ruins your accuracy. On the other hand, a random error, like maybe a parallax error when reading a scale from slightly different angles, scatters your readings. That reduces your consistency, which is entirely about precision. Just look at these archery targets. They perfectly illustrate the difference. They show systematic errors, where the arrows are grouped really tightly but miss the bullseye completely, versus random errors, where they're just scattered everywhere. You also have to make sure you're matching your instrument's resolution to the task. Using a meter rule for a large object, but grabbing a micrometer screw gauge for something as fine as a wire's thickness. Now, the absolute most crucial point here is knowing exactly how to combine uncertainties. This is non-negotiable if you want full marks. If you're adding or subtracting quantities, you add their absolute uncertainties. But if you're multiplying or dividing, you have to switch gears entirely and add their percentage uncertainties. Mixing these up is an instant red pen from the examiner, for sure. Okay, Section 2, Solving Turning Effect Problems. Let's move to our next syllabus hotspot and see how we transition from simple measurements into dynamic, structural physics. A super common, fatal mistake here is using the wrong vector approach or failing to define key terms before answering extended responses. Examiners constantly warn us about contextual misapplication, like misaligning a force factor and terminology confusion. If a question asks about the torque of a couple, you literally cannot just vaguely define a moment. You have to be incredibly precise with your language. What's really interesting here is the exact problem-solving sequence examiners actually want to see on your paper. Tracing this path guides you completely away from those top examiner warnings directly into a bulletproof strategy for your calculations. If you follow these 3 precise steps, you lock in those process-based marks, even if your final arithmetic is slightly off. Step 1, deconstruct the tangled forces and identify the relevant variables. Step 2, apply the method mark strategy by executing your analysis with clear notations, like writing out explicitly that the sum of torques equals 0. And step 3, verify and present. Double-check if the answer actually makes physical sense and use proper formatting conventions. Moving on to Section 3, Conquering Capacitors and Alternating Current. Now we're entering a really high-stakes zone that connects multiple complex theories. This is right where top-tier students separate themselves from the rest of the pack. Think about this for a second. Why does this one specific area carry so much weight? The answer lies in how examiners use the time constant to test your ability to integrate cross-topic knowledge. They aren't just testing capacitors here, they're testing your fundamental grasp of exponential decay, electrical fields, and energy transfer all at the exact same time. It's like a giant puzzle. Take a moment to just absorb how the theoretical foundation of tau equals RC branches into strict procedural frameworks. You can literally see how the cognitive domains of knowledge, application, and analysis all stem directly from that one central formula. This right here is the blueprint for how a principal examiner writes a question. So, never jump into the math without first satisfying the knowledge and understanding domain. You have to define what the time constant actually represents in that specific circuit. The time constant is the time taken for the charge, current, or voltage to drop to roughly 37% of its initial value. State that magic 37% clearly before you start frantically plugging resistance and capacitance values into your calculator. Shifting over to alternating currents, this perfectly isolates the connected understanding you need to avoid the trap of providing naked numbers with zero scientific reasoning. Compare a flawed student answer to a top-band answer. The flawed answer just dumps the math, right? Like P equals 0.5 times 200. But the top-band answer actively explains why, connecting the concept that mean power is half the maximum power for sinusoidal AC, citing the evidence from the graph, and then doing the math. 0.5. Remember the simple decimal, because for sinusoidal AC, the average power is exactly half of the peak power. That is the absolute cornerstone of your method mark strategy. It's such a simple multiplier, but skipping the logical step of explaining why you're using it, that's exactly how students lose out on top grades. Seriously? Don't skip the logic.
Let's jump to Section 4, Packing Efficiency in Solids. We're going to step away from the circuits for a minute and zoom microscopically into our next core concept. This is a brilliant example of how macro-level material properties are dictated entirely by invisible, microscopic arrangements. To avoid losing marks by just throwing around vocabulary terms, we need a layered cause and effect walkthrough of packing efficiency. The examiner doesn't just want a label, they want to know what the physical effect is inside the solid and why that matters for real materials you can actually hold in your hand.
If you construct your exam paragraph following these 4 precise stages, you demonstrate a deep, unshakable mastery of crystal structures. First, define the physical picture in everyday language. Second, describe the microscopic mechanism using technical vocabulary. Third, identify what measurable consequence this has, like, say, changes in energy or structural integrity. And finally, connect it to reality. A disciplined paragraph connecting cause and effect is always going to outscore a scattered list of memorized facts.
Connecting the microscopic mechanism to one of these real-world materials makes the physics memorable and secures your application marks. For example, the way atoms pack together totally determines the defect tolerance in structural alloys used for aerospace, or the electrical properties of semiconductor wafers. It's not just theory, it's literally the foundation of modern technology. And finally, Section 5, the final exam challenge. Okay, it is time to see if these concepts have truly locked into your memory. We've covered a massive amount of ground today, from micrometer measurements all the way to atomic crystal structures. So let's put your recall to the test. What are the top 3 mistakes an examiner will immediately penalize you for in a multi-step calculation? I'm going to give you 10 seconds to pause this explainer, picture our earlier concepts, and lock in your answer. Think back to the alternating current roadmap and those warnings painted in red. What are the 3 specific traps that strip away method marks? Go ahead and pause now. Did you get them? If you avoided those 3 traps, you are well on your way to an A-star. You absolutely must format properly, check your presentation, like using the correct significant figures, and explicitly tie your reasoning to the exact context of the question. So the next time you look at a simple everyday object or a complex circuit, ask yourself, can you visualize the invisible physics happening beneath the surface before you even try to calculate it? Keep visualizing the physics, and I promise you the math will follow. Thanks for tuning into this explainer.